This presentation covers the reactor simulation that we all did earlier in class. We are Team 4 from Fundamentals of Nuclear Engineering, Spring 2018. In this exercise, we only vary control rod position. As the control rod position is changed, a change is seen in the reactor's power output, coolant temperature, steam pressure, reactivity, and turbine demand. As is expected, the neutron absorbing control rods slow down the nuclear reaction as they are lowered in between the fuel rods. This leads to less thermal power output of the system. In answering question 1, we found that the pressurizer pressure stayed the same, but the percent level of it did vary with temperature change. The temperature stayed around 600 degrees Fahrenheit, but we did see a variance of that temperature about 10 degrees. The temperature drops as the control rods are inserted because the nuclear reaction is slowed, transferring less thermal energy into the system. The pressurizer serves to keep the coolant from boiling. With decreasing temperature, we see the pressurizer level drop as there is less demand to control the temperature. As for question 2, when the control rods are inserted, the reactivity changes by a magnitude of 0.001%. A negative sign there indicates that the rate of the nuclear reaction has decreased. Once steady states are reached, the reactivity will return to 0%. At steady state conditions, we see our K values of 1, which is at criticality. Immediately following equal changes in rod position, we will see a 0.001 change in K values.
In exercise 2, we varied only the turbine demand. As the turbine demand is changed, we also see a change in the reactor's power's output, coolant temperature, steam pressure, reactivity, and rod position. Though there is changes in these values, the changes are not as substantial at first glance. The main changes come from the coolant temperature and the steam generator pressure when comparing to the reactor leading simulation. The coolant temperature with turbine leading only drops to about 604 degrees Fahrenheit, while it drops down to about 599 degrees Fahrenheit for the reactor leading simulation. Additionally, the steam generator pressure for the turbine leading goes as high as 847 psi, while it goes up to 853 psi for the reactor leading simulation. For the reactor power, the reactor leading dropped to about 75%. In turbine leading, the reactor power at its minimum dropped to about 84% of its max power. Thus, changing the reactor's control rod position seems to impact the reactor's outputs much more than by changing the turbine demand. This is because the control rods physically change the criticality of the core, while the turbine demand changes the desired power output.
Using turbine demand to control reactor power would not be as effective as using rod position. By just using turbine demand, the criticality of the core is not directly controlled, which poses the risk of energy buildup in the reactor. Using control rod positions, on the other hand, allows for the criticality of the reactor to be directly controlled, which also acts as a safety mechanism to shut down the reactor if unusual behavior is detected. Going further, we can compare the plots of core thermal power versus time for both the reactor leading and turbine leading scenarios. Controlling reactor power should be a smooth and slow process, which is exactly what the plot for reactor leading shows. If we look at the turbine leading, however, the change in power is very rapid and not ideal for a reactor.
In exercise 3, the reactor is tripped, and all the effects of the trip on the rest of the system are observed. Once the reactor is tripped, all of the control rods are placed inside the reactor, causing the reactor to shut down in about 3 seconds. The control rods are excellent neutron absorbers. This reduces the nuclear fission inside the reactor drastically, which in turn reduces the reactor power as shown in the core thermal power and fuel rod average temperatures. The heater power surges and begins to dissipate as the reactor cools. The steam flow follows in decrease alongside the dissipation. Overall, the trip causes a decrease in reactor activity due to the location of the control rods being displaced.
For the second problem, the heat transferred out of the reactor cooling system is 1785 megawatts. When compared to the normal operating condition of 3400 megawatts, our value is roughly half. During normal operation of the reactor, the thermal power from the fission dominates. After the control rods have been rapidly inserted into the core, the number of fission reactions will decrease. This decrease of fission reactions will also cause the thermal power to decrease. We have reached the end of our presentation. We hope you guys enjoyed it. Thank you for your time.